All right, guys, welcome everybody. Good afternoon. So this is Lab 5, Week 6. Today we are going to look at TCP/IP based attacks. So in this week and the next week, we have TCP/IP based attacks. All right. So you can say this is part 1 of TCP/IP attacks, where we are going to go through 3 different tasks today. So the first one is called SYN Flooding. Okay. Just to give you a little bit theory of SYN Flooding. Everything in the network actually relies upon one of the reference models. So there is a reference model called OSI reference model. Does anybody know how many layers are there in OSI reference model? Yeah, 7. So let's divide it into 7. 1, 2, 3, 4, 5, 6, 7. Okay, good. So there are 7 layers in OSI model. That's good. But do you know their names? What is the first one? This one. What is the first one? Physical. The second one? Data link. Right. Then the third one? Network. Then you have transport. Right. Please do not throw sausage pizza away. That's how I remember it. Physical, data, network, transport, session, presentation, application. All right. Okay. Now, we are looking at a TCP attack. So in TCP, do you know which layer this protocol belongs to? TCP? Transport layer. Okay. Transport layer, exactly. So what we do as a human, we always interact with the application layer. You're always like when you're using the web browser, you're interacting with the HTTP. When you're using, any email, for example, you're dealing with SMTP or POP3. So as a human, we're interacting with the application layer indirectly, right? So that's the closest we get to the OSI model. And then your data is actually encapsulated. The application layer will put its header, it will pass it on to the presentation layer. Presentation layer will put its own header and pass it on to session layer down to the transport. Now at the transport layer, you will have to make a decision. What do you want to do with this data? Do you want to send this data as a reliable data? Okay, so you choose whether you want the data to be sent reliably, or you want to send this data without reliability, non-reliable. Okay, just let's call it non-reliable. Okay, so at this layer, you make that decision. All right, so if you are choosing the reliable connection, you are using the TCP protocol. All right, TCP protocol is reliable. All right, what does that mean? Whenever you send anything to the other party, you wait for the acknowledgement. Okay, if you don't get the acknowledgement, you resend it. All right, so you are actually waiting for the acknowledgement. That's a reliability factor there. If you are going for non-reliability, you are actually opting for another protocol, which is UDP. Okay, so when you go for TCP, you get reliability, that's fine. But, what do you lose? You lose the speed there because you are adding extra overheads, right? When you go for TCP, you want extra reliability, all good, but you're losing on to something. You're losing the speed because you have extra overheads to take care of your reliability issues. Okay, so this will be slower, but you get reliability. In UDP, you don't have reliability, but this is faster. Okay, so you use it in the application or in the scenarios where you don't care about the reliability, you just care about the speed. For example, right now I'm speaking on the Zoom with you guys, video conferencing. It's using UDP. Okay, because if it waits for the acknowledgement for every packet it sends, imagine there will be jitters and delays, and my voice will not be clear to you. There will be a lot of delays in there basically. So yeah, there you have. So the TCP attack, which we are going to do today, or TCP protocol, uh, has one of the type of packet, which is a SYN packet. All right. So TCP uses SYN packet. Then it waits from the, we call it client, let's suppose the server. So client is sending the SYN to the server sends back you SYN with the acknowledgement, both fields are one. And then you again send an acknowledgement packet, okay? And after the exchange of these three types of messages between the client and the server, your session is active, and then you send your data on top of it, okay? So everything you send on TCP has a session first, and then you make a request and you get your object, and you then, like that. Okay. So SYN is one type of TCP frame, all right? And we are looking at layer 4, as you said already, right? So TCP is a layer 4. That's what we're going to look at. We are going to look at this timeline in more detail when in the one of the slides. I'll explain it to you there as well, how SYN actually looks like in the timing diagram. By the way, you can download these PowerPoint slides. They're already on MS Teams. So you may want to go ahead on the Teams, download this PowerPoint slides. That will help you. Okay, so that's the first attack, layer 4. All right. Second, which we are looking today is the TCP, cache poisoning. Very interesting one. And yeah, it's actually a very, very powerful attack. SYN flooding is more like a DOS attack. We will again, as I said, when it comes to the slide, I will explain it to you furthermore. But right now we're just looking at what layer are we targeting in OSI model, okay? Just to give you a very brief overview of what are you actually going to do today. So again, in OSI layer, OSI model, you have 7 layers, right? 3, 4, 5, 6, 7. And ARP, just focusing on ARP. What does ARP means, anyone? You have done all this in network fundamentals, I'm sure. What does ARP means? ARP, come on. Address resolution protocol. Yeah, you can send to everybody, Shannon. You don't have to send private message for that. Okay, yes, cool. So ARP is address resolution protocol, not MAC address information. Half that's anyway. So yeah, ARP stands for address resolution protocol, right? So what we do is in this, we are actually mapping layer 2 addresses with layer 3 addresses, okay? What is a layer 2 address? Name any layer 2 address, MAC address, physical addresses, they are MAC addresses, right? What is a layer 3 address? IP address, okay? Now, IP address are also called as logical addresses, right? They're logical, right? They're not physical, okay? So layer 2 is a physical address. What does that mean? A MAC address or a physical address is something which is burned on to your network interface card. Any device which wants to connect to the internet or which wants to connect to you wirelessly or in any way has to have a MAC address. Okay, so that is a unique address. That's permanent address, like your fingerprints. Any device who has that address, nobody else will have that address in the world. Okay. So MAC addresses, how big are the MAC addresses, guys? What are the size in bits? MAC addresses are 48 bits long. Okay. MAC addresses are 48 bits long. What about the IP, you have IPv4, IPv6, but we are just focused on IPv4. How big are IPv4 addresses? 32 bits, yeah, exactly. So we write the MAC addresses in the base 16 hexadecimal, and we write the IPv4 addresses in base 10, right? Okay, so ARP is nothing else but just a mapping of layer 2 to layer 3. Okay, what does this mean? This means that the devices in a network, they actually keep track of or information of their neighbors. Okay, again, the important thing to note here is that ARP is based only in a network, in a local area network. So for example, you have a network here, all right, and then you have a router, I don't know, for example, this network is connected. And in this network, you have one PC, two laptop, another mobile phone, iPad, your smartwatch, whatever. So this is a network, one network. Everybody in this network has the same network address, okay? And then somewhere you have another network where there are different devices, and they are also, of course, they are in a, that's a local area network, another one. But you are connected through a router, okay? And remember, a router can connect only to dissimilar networks, okay? That's the job of a router. You cannot have same networks connected to two different ports of the router. But anyway, the point here is ARP is confined to one network only. Okay, it will never cross. No. Okay. So the devices in this network will keep information about each other. They don't keep information about the other devices on the other network. Okay, it's just local area network. That's it. Okay. So all the devices here will have a mapping of layer 2 to layer 3 about each other. Okay, so this, let's suppose this is device 1, 2, 3, 4, 5. And if you go to device 1 and you see device 1 will have the information about device 2, 3, 4, 5, 6. Okay, so that will be on device 1. Device 1 knows about device 2, sorry, device 2, device 3, 4, 5, and 6. So it knows about everybody in its network. So let's suppose these are the IP addresses of its neighbors in a network. And let's suppose these are the MAC addresses. So it will have MAC addresses like, let's suppose A, B, C, D, okay, E, anything. All right. Just excuse my writing. I'm just using a pen, mouse. So yeah, device 1 knows about all the devices in the network. Similarly, if you go to device 2, it will know about its neighbors and everyone in the, provided they have actually communicated with each other. Okay, otherwise they don't know by default. They have to actually learn about each other. Okay, they have to learn about each other. But the point I'm making here is ARP is address resolution protocol. It resolves the addresses for you. The devices keep the mapping of layer 2 to layer 3 in their ARP table. Okay, you can call this ARP table. You can call this MAC address table. Okay, anything. But that's what it is. Okay. All right. Now, when a device, a source wants to send any message to the destination, right? The source creates an Ethernet frame, okay? And when you see the Ethernet frame, I'm not going into the details of it, but there are fields in Ethernet frames. One of them is a source IP, one of them is a destination IP, right? So source already knows that its destination, whether it is in the same network as it is, or it is in a different network, all right? So let's suppose I say this device wants to send message to this device, all right? Okay. Now this device already knows as it creates a frame that, hey, I am 1111 and I'm sending message to 2222, okay? As soon as it creates the frame, it knows 2222.2.2.2 is not in my network. So what does this device do? The source, it always use the MAC address of the gateway. So it will send the packet directly, I mean, yeah, it will put the destination MAC address of the gateway. Okay, so the packet will go to the gateway, and then the router will decide where to send, and then it will be forwarded out to this destination. So the point is, as soon as the source creates this Ethernet frame, it knows the device is inside the network or outside the network. If the device is inside the network, they only use layer 2 and that's it. Okay, they communicate using MAC layer addresses. Okay, MAC addresses. If the device is outside, they still use MAC address, but they forward it to their gateway. Okay, and then onward it's layer 3. Okay, now ARP is only inside the network, remember, okay? It's confined in the network. So yeah, I think, and ARP is layer 2, all right? This happens at MAC layer. In the data link layer, there are 2 sub-layers, LLC, which is mostly for the session step and access, the session establishment, and MAC layer is the second layer. So this ARP refers to that. So you can say that the SYN is for layer 4, the ARP is for layer 2, okay? We will look at how we will be poisoning it, okay, in much more detail in the coming slides. Any confusion so far? Any questions you have? Any interesting ideas to share? 38 people are there. At least some questions should be there. No, all good. Okay, good. Okay, so these are the 2 tasks. And then the third task we will be looking at is ICMP redirect. Like everybody has some favorites, right? So this one is not my favorite. ICMP is a very, very like, you can't actually harm that much using ICMP. That's what I mean to say. It's not very interesting task. But anyway, the theory behind ICMP stands for Internet Control Message Protocol, and you use it all the time, guys. If you don't remember, this is a protocol which is behind your ping. Whenever you're pinging any destination, that's the protocol you're using, ICMP. Okay, it's mostly used for troubleshooting, right? What are you doing as a source? You are sending a packet to the destination, and you're checking whether you have that connection with that device, right? Is it working or not, available or not? Okay, simple. Just checking if the other party is linked with you, connected to you, right? Redirect, as the name suggests, it's very obvious, but let me put it this way, that whenever you're pinging between your source and destination, it can go through a couple of routers. It doesn't have to be direct, right? It can be 1 router, 2 routers, 3 routers, you don't know. But the point is, it takes the shortest path possible, right? So it will go to the destination and come back to you within that TTL. You have time to live, right? Anyway, so it takes the shortest path, but redirect happens sometimes, and it's a genuine case. When can it happen? It's just like we are driving on the road, or walking on the road, and there is a construction work going on, and you have to take a detour, okay, from another street maybe, just like that. So the packet is going to the router and the other router, and this router says, no, the link further is not working. You have to actually go to this router and then come back to this link. You know what I mean? So it's just like a redirect, right? Maybe traffic is busy or whatever. So this is a genuine function of ICMP, but we are going to exploit it. Okay, we are actually going to force the source to take a deroute and come to us as an attacker and then go to the destination. Make sense? Okay, so that's all we are going to do. So as you can probably sense, it's not a very powerful attack. It's just ping doesn't have a data in it. Ping is just a packet going to the destination and reply coming back. That's it. It doesn't have a data in it, right? So it's not very useful in that sense. Okay. But yeah, you can actually make the source wait longer by redirecting the packets, or you can just see who is connected between that source and destination. Okay, you can see that, okay, this guy is 2.6 and this guy is 2.8. You know, you can know the IP addresses. Yeah, any information can help. But this attack is not as strong as these two. Okay, I hope that makes sense. And ICMP works, it uses IP addresses, right? So it's, yeah, layer 3 address, layer 3. Okay. So now you know your attacks and where they belong to in the OSI model. I hope that makes sense to you. And it will be much more interesting when you are going to actually see them in action. Any questions, guys? Any questions? Was this any interesting? Did you like the theory? Yes, no, anything, you know? It's like I'm talking to my screen. Okay. Hope you guys can hear me. Hello. Okay, let's move on. See that X now. First thing first, you have to actually turn on all the virtual machines. So please do that. Or you do that, and I'm doing it for this lab as well. Just logging in. Okay, you can see I have already done something with the previous class. I'm gonna quit it. Quitting, good. I'm just gonna quit this as is. All right. That's my client. Going to the need it. That's my client. That is a server. Let's log into the server as well. And the attacker. Everything. What is this for? And same here. Okay. Yep. So everything is working. Now I will make sure that my Wi-Fi is disconnected here. And all good. CyberSec server. Okay. So just do that. Go ahead and disconnect the Wi-Fi on your server as well. Another thing which you should note, and you know, it's always helpful to know your network. You have a network of server, attacker, and client. Okay, SAC. Just remember it like that. SAC. Okay, 678. 678. 6 is your server, you know, S. A is your attacker, 7. Client is 8. SAC. Okay. All right. So this will always be your network anyway. So you go to the server first thing first, disconnect the Wi-Fi, make sure it is disconnected, verified, and let's take a look at the tools which you're going to use today. So you have been using Wireshark, you have been using NetWag. Today we will be using a new tool which is same as Wireshark, no difference, other than this guy is on a CLI based. Okay, it's actually command line interface, and you have your Wireshark, the graphic user interface. Okay. Now, why are we using T-Shark is because for the first task, which is a SYN flooding attack, when you launch SYN flooding, it will bombard the target with so many, you know, thousands of packets in milliseconds that it will bring the Wireshark down. So Wireshark is not an ideal choice for that. Okay. That's why we rely on T-Shark for that. It's the same thing, it's packet sniffer, but it's much more robust. Okay. And you have been using network all the way. Okay. Let's take a look at TCP, how TCP works. Okay. So focus on the left side now for as a first point. This is how a TCP session is created. So as a client, let's suppose this is a client user. User sends a request, okay, the SYNs to synchronize with the server. If the server is available, the server will send back a SYN ACK packet that say, yeah, okay, let's connect. And then the user will acknowledge, okay, let's do that, okay? So you go through these 1, 2, 3 steps, which we call it as three-way handshake, okay? And once everything is okay, all good, then you guys are connected with, okay? The server and the client is connected. And on top of this, you start sending the data, you start exchanging the data, okay? So once you have to establish the connection and then on top of that. So this is a normal TCP, okay? SYN, SYNAC, ACK, all right? So you start with the SYN. If the server is available, it sends you acknowledgement and then you send acknowledgement and that's how you connect. But you see, this is a normal behavior. Let's see how it looks in the attack scenario. As an attacker, you take the advantage of this SYN and you send so many SYN packets to the server, okay, that it brings the server down. Now see, server is just like any other device, right? It has a resource, it has a limited resources. It has a memory, which has a limit, okay? If you are going to send thousands and thousands of SYN packets in quick succession, the memory will be overwhelmed, right? It will full, okay? So the server will not have any more memory available. Okay, even it doesn't even reply back. It doesn't have anything left to even reply back. So if a genuine user comes in meanwhile and sends a SYN packet, which is a genuine SYN packet, and the server cannot respond, right? Because it's already full. So you see the message like your website is down, no connection available, try again, you know, these messages. So this is actually a same scenario as DOS attack or DDoS, all right? Where you are actually bombarding the target with so many SYN packets, hence bringing your target down, okay? Overwhelming it the packets. This is what we are going to see in the reality now. We will, as an attacker, send so many SYN packets to the server, okay, that you will not even see this packet back. Okay, all right. So that's your attack. Let's take a look at this. Let's launch it. So first thing, since we are using T-Shark, so let's go to client and start the packet sniffer. Okay, so let's go to client, server attacker client, go to the terminal and launch T-Shark. Put the password. I always make that mistake. The right password, and there you go. You don't have to do anything. It will start capturing the packet all automatically from Ethernet 0. Okay. So go to client, run T-Shark, and that's it. All right. Now let's launch the attack. We go to the attacker. Okay. Launch the network attack library. Find out the relevant attack tool, 76 in this case, SYN Flood. Let me do that. So we go to the attacker, and for some reason I can't find my maybe terminal. All right, and I will launch back. Okay, server-sec, and I want SYN Flood, right? SYN Flood 76. Double click it. Okay, so I want to actually target the, let's suppose in this case, we are targeting, the client. So let's target the client 10.0.2.8. Okay, all right. Now be very careful, guys. I'm not running it at the moment. Let me actually make it a little bigger because, it doesn't look neat on 2 lines. Okay, that should be enough. Make it bigger so that everything is on 1 line. Okay, let's go to attack and see the client as well at the background. As soon as I run it, so I'm actually running a slow PC, which is my another computer, and I'm, virtually using the remote desktop so that I will see very slow connection. You guys should see this, very fast actually. So as soon as I run it, you see it's running, but please don't let it run longer. Just interrupt after 2-3 seconds. That's it. Okay. All right. Okay. So let me just quit it. Um, all right. Now, if you go back and you see it has already sent tens of them, and yours will be much faster. As I say, SYN packet, SYN packet, SYN packet, SYN packet, SYN packet, SYN. All you see are SYN packets, and you see the source IP is different. Destination is always client. Source IP is different. Destination is the client. You see, it's like a DDoS attack. All right. Everybody is sending to the client what SYN packets, right? So you can't see any SYN ACK here. All of them are SYN, 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 SYN. There is no time for the machine, for the client in this case, to reply back even. All right. Please don't let it run longer, otherwise it will bring your virtual machine down. And yeah, that's it. You see, this is the proof. You have launched, bombarded the client with SYN packets. The client cannot even reply back. This is just an extra. Okay. So once it is done, I just want to close my Wireshark. That G-Shark, and that's it. Okay, so that's your first attack. Go ahead, do this. Let me know if you have any questions. I'm just gonna pause the recording. All right, so that's great. You have done the first task. Good. Now, ARP Cache Poisoning, right? One of my very interesting attacks. Okay, let's take a look at the theory first. What ARP stands for Address Resolution Protocol, and I've discussed enough about it. And I said it is about the host or the devices keeping mapping of layer 2 to layer 3 within their network. Okay, within the network. What do I mean actually? Let's actually do one thing. Go to the packet tracer this time. Packet tracer. Talk a lot about, right? I use this name instead of Wireshark a lot. Okay, let's see something in action here. I'm just going to bring up two PCs, connect them together, and give them IP addresses, of course, because without IP addresses, there is no point. They need to have IP address, right? Every device need to have an IP address. So let's give them names. On an IP address. Okay, so this is 1.2, the other one is 1.1, and they're in the same network. Okay, so now these devices have been just been connected. All right, they have no idea about their network. So what does that mean? PC0 does not know about PC1. PC1 does not know about PC0 because they have not communicated with each other, right? It's just like two people coming to the room and, it's strangers coming to the room. That's it. Okay, they don't know about each other. They have to talk. So if you go and you want to check, there is a command which you can use to check what this device knows about its network. So that command is actually the same on the Windows machine, the Linux. Everybody uses the same command and the same key. ARP -A. Okay, this will actually pull up your MAC address table or the ARP table. All right. A means all. Anyway, you can do a question mark and read about that further. Similarly, if you go to PC1 and you write this command on PC1, you will know how much PC1 knows about its neighbors. Okay. So far, these are the two neighbors only. They haven't spoken to each other, so they should not know about one another, right? Let's take a look and verify that. Let's go to the PC0 command prompt and write the command ARP -A, and you see no ARP entries found. So PC0 does not know about PC1. Similarly, if you go here, you do the same ARP -A and same, so they are unknown to each other. Okay, because they haven't communicated. Now, when you force the communication between them, let's ping from this machine to the first machine, 1.1. Okay, so 1.1 is PC0. I'm pinging PC0, so I'm actually forcing a communication. Okay, I'm asking them to talk to each other. So as soon as they start talking to each other, I think there is something wrong, maybe an IP or something, but anyway, you can have a look. Shouldn't be that slow. There's definitely something wrong. Let's take a look at the IP address. 192.168.1.2/24. We put the wrong IP here. 192.168.1.1. Oh, everything is good. Okay. 192.168.1.2. Am I reading it wrong? Anyway, let's try again. 191.68. Okay, let's take a look here. Oh, I put 186. Sorry, one time. Okay. Okay, let's go back and ping. You can ping from anywhere. Pinging again. There you go. Reply is coming. Now we have forced the communication. Okay. Now PC1, PC0 has exchanged some packets. Okay. Now, when you exchange packets, you can only exchange it successfully when you have the addresses. Okay. So now if you check their MAC address table or the ARP table, you would see that yes, the PC1 knows about PC0. Okay, this is the IP address of PC0 and this is the MAC address of PC0, right? So there you go. You have layer 3 to layer 2 mapping for the entire network. That's the entire network for a PC1, right? For PC1, PC0 is the only network neighbor. Okay, so similarly, if you go to now PC0 and because since they have exchanged the packets, PC0 will know about PC1 as well. So that is what they did. The first packet is lost in translation. They will do ARP. Okay, make sense? Okay, now how will we utilize this? How is this beneficial to us for this task? Okay, let's see. These are only two IP addresses. I mean, these are only two PCs. Okay, if you have, let's suppose, 5, 10 PCs connected, this makes it much more interesting. But imagine they are connected, okay? So this PC0 will have the IP address of all of them, right? IP MAC, IP MAC, IP MAC, okay? It will have eventually after they communicate. So PC0 knows about its network and this is how it will look like, okay? What we will do is, as an attacker, okay? We will actually send an ARP message, okay? And we will say to, let's suppose PC0, we are saying, or everybody, you can send it to everybody and say that, hey, this 19, for example, okay, let's take this example, say, okay, this 192.168.1.2, that is actually my MAC address. So you're sending the ARP, you are not changing L3. Remember, this is not a layer 3 attack. It is layer 2 attack. You are spoofing layer 2, okay? You're saying that, hey, 192.168.1.1 or 1.2, that guy, and you're sending your MAC address. You understand? So that this guy saves as that mapping. Okay. Now, how is this useful? It is useful because when the devices communicate within the network, they speak the language of layer 2 only. Okay. And next time if anybody is sending anything to PC0, they are actually sending it to this guy, attacker. because they have their MAC address saved against its, IP. Got the idea? It's a very powerful attack. So you are actually spoofing to be someone else. And this is one of the drawbacks of ARP, because ARP does not have any authentication. Okay? ARP doesn't have any authentication. This is very, very, one of the very big vulnerabilities in ARP. So anybody can come and say, hey, I am Blake, I am Amin, right? So yeah, within that network, you can easily spoof it. And similarly, you can go to the router and you can tell the router, or you can, you can take the IP of the router and put your MAC address next to it and send everybody. What will happen? Anybody who is trying to reach the gateway will actually go through you then. Okay. Yeah. So this is, I hope it makes sense. Any questions, please let me know. We have enough time to discuss all this. Questions have to come from you. Okay. I'll take that as a good. No questions, shut it down. Okay. So that is cache poisoning. Okay. We will see that in action now. So yeah, this is all the theory I've explained to you. What is happening? This guy is looking for the IP address of this, MAC address of this person. And it's not 000, it should be FFFF. When you broadcast, you are actually sending everybody. So this is the information of this PC itself. And this is the IP of the target, which it is looking for. So it sends to everybody. And this guy says, no, that's not me. This guy says, no, that's not me. For example, this is the IP address of this PC. So this PC will reply back with its IP and MAC address. And then that IP MAC address will be saved here. Okay, that's how ARP works. Very, very simple. So it's sending request to everybody. This person replies back and it updates its MAC address table. Now, attack scenario is like this. Attacker says, the attacker is playing double game here. In this case, attacker is sending ARP to router saying that this victim is actually me. Okay, so attack router will think that attacker is actually the victim. And it is also sending the victim IP and IP address of the router and saying the victim that if you need to send anything to the gateway, that is me. So victim in the future, with anything it sends to the router, it will be sending to the attacker. So attacker is actually coming in the middle of the switch, the router and the victim. So this is man in the middle attack using ARP. Okay. I hope you get the idea. All right. So this is just an explanation. And as I said, there is no authentication in ARP. And you can read about this. I've already explained that to you. Let's start. So first thing first. First thing, we have to verify everything is working fine originally. Okay, originally. So we go to the server and we find out how much server knows about its network. So we went to the server and we type in the command, right? This is a command which will tell us how much the server knows about. So the server knows about 2.8, right? And 2.7. Very good. This is all we want. Just ignore this one. It's a virtual Ethernet. Okay, so we actually want server to know 8 and 7, right? Server itself is 6, remember? SAC, right? SAC 678. So this is 6. We are standing on 6 and we should know about 7, 8. And that's where we rightly know about 7 and 8. And this is their MAC addresses. Okay. So if any of you going to the server is not able to see the IP addresses and MAC addresses like this, you need to do something which I told to my first group today. And I did that for them. You delete your images. You have the copy of the downloaded zipped file, right? Okay. My recommendation is for every lab, delete your used images which you have used in the previous labs, delete them completely, unzip and use the fresh copies. You don't have to download again and again, just the zip version, unzip it and use them again. Okay. If you do that, you will see it will work. Okay. So if you're not able to see this, it will all it will take you 3 to 4 minutes. Delete the current images, unzip the fresh copy, and use the fresh copy. Okay. All right. So this is what the original is. Now, what are we going to do? We are going to change this MAC address. Okay, we are targeting the client. We will change this MAC address. For now, it doesn't matter any MAC address, right? But to make it effective, this MAC address has to match the attacker's MAC address, right? But anyway, for now, you just, we were just going to spoof this MAC address to, poison it to any other. Okay. So the server will think that, okay, 2.8 is actually AAA, BBP, or whatever you have written, not this. Okay. So that's the whole task. Let's go on and do that. So this is a attack. This is a position values before the attack. We go to the attacker. We launch the attack number 80, periodically send ARP replies. Okay, we say that, okay, this is the IP, this is the MAC address of the client. We are making, we are filling the wrong information, wrong MAC address. So we are saying the client is actually this MAC address. This is the map you should be using. And we send it, run it. And when we come back to the server and check it after the launch of attack, we see, the MAC address is changed. Now, anything in the future, MAC address, the server is sending to 2.8, it is actually sending to this MAC address. So let me do that for you. Let me go to, where is the server? Okay, so this time going to the server. I don't know why my terminal is there. Go to the terminal, sudo. We want to actually look at the table. There you go. Sweet. I have 7 and 8 there. Good. I'll go to the attacker now. Launch the attack. Very simple attack, actually. Just launch the attack, which is ARP something something, and okay, yeah, number 80. And I say, okay, actually, the IP address is 010203. Sorry, the MAC address is 010203. And client IP is this one, and this is the MAC address, okay? And I run it. That's it. I go back to the server. Server has already learned, the new one which has been sent. And when I up to it, and there you see, yes, it is in action. Change, right? It has been changed. Yeah. Good. That's your second attack. So go ahead, launch the attack, see that in action. And if you have any questions, let me know. Okay, so the third task is ICMP redirect. Okay, it's just that when you're pinging between two devices, it takes the shortest path to go to the destination and come back. In case of a redirect, genuinely, it takes a redirection. That's it, depending upon the scenario, maybe the path is choked or the link is down, okay? But we are going to actually take, improvise on that. We will exploit that actually and force a redirection, all right? Okay, so for this task, it's not a heavy duty task like this task one. So Wireshark is perfect. It actually gives us more insight. We can actually read the headers and all that details. So Wireshark is perfect. We will be using Wireshark. So go to the client Wireshark and filter it for ICMP traffic. Okay, and just do a ping from yourself as a client to the server and see what does a normal packet exchange looks like. Okay, so let me do. So I'm going to the client, closing the server thing, and we'll need attacker. Okay, let's go to the client and launch Wireshark. Okay, put in the password, all good. Okay, get that, Ethernet 0, start, and I'm just gonna put this a little bit down, and this one as well, and put a filter of ICMP. Oops, press the wrong key. Enter. Okay, there you go. So neat and clean, right? Okay, now let's go to the attacker. Oh, let's actually try a simple one here first, the genuine one. Let's see how the normal ping looks like. Okay, so 10.0.2. So we are client, we are pinging the server. Server is 6. As soon as we ping, I'm going to actually stop it. I'll Control C. And yeah, you can see at the background on the Wireshark, the client is pinging the server. Server is replying back. Okay. So we are sending the request. We got the reply. Everything looks good. Okay. So it will always be request, reply, request, reply, request, reply. That's ping, right? So that's the normal scenario. Everything looks fine. Okay. Now let's go back to the attacker, launch the attack, and we want the ICMP redirect attack. So let me actually put another keyword, redirect. Oops. Redirect. There you go, 86. So we are using the tool number 86. Okay. And okay, we use Ethernet. We are adding this gateway. We are saying that 6 to 8, take a redirect to 7. Okay, we use best. And use the source IP as any, maybe source, okay? Because it's a ping, it's two-way anyway, it doesn't matter. You can use 6 and run it, right? Okay, keep it running. Go back to our client and run the ping command again. This time, okay, I'll just stop it again. You know, it has already ran. And you see at the background, we have ICMP redirect, okay? It is still showing 6 to 8, okay? But if you look at the client, where is the client gone? Oops, I've closed that, haven't I? Okay, if you look at the terminal, you can see one thing here that it is showing you there is a new hop that is, and there is a redirect as well. This is your first proof, okay? Secondly, you can go to the packet tracer and you can highlight this as your second proof, all right? And normally it should show but anyway, if you click on this packet and you look at the headers of this packet and you specifically, I'm just going to make it a little bit lengthier if it allows me to. Why? Yeah, okay. So if you look at this ICMP, come on. So I'm selecting this packet, any redirect packet, and you look at its header, all right? You see, the important thing here is you have type 5. It is a redirect, confirm. Vaishak is very good in explaining that. And plus, you can see that there is a gateway address, 2.7. There you go. What else? You have solid proof, 1, 2, 3, another one on the terminal 4. Yeah, perfect. So you see, nothing can hide from Vaishak. So it has been redirected to this gateway. Okay, perfect. Let me actually go back and shut down my attack. Yeah, don't want to run it. as well. Everything is good. All good for me. Okay. So that's it. That's ICMP redirect attack, guys. So you go to sudo network, you launch attacks 86. In the details, you put the gateway is already there probably. You're choosing the best initialization type, and you can choose either source 6 or 8. That doesn't matter. As soon as you run it, you can see 1, 2, and then further. I recommend you go into the ICMP header as well. Okay. And the type 5 is a redirect type. So a little bit of theory. If you just Google types of ICMP messages, you will see there are 50s of them. But we are interested in type 5. You see, it's a redirect message. Okay, that's the proof. We saw it in the Wireshark as well. Okay, that's it. And just on the last note, very important announcement. Most of you have submitted the weekly lab tasks. Very good. I'm proud of you. You have done a wonderful job. Just as a reminder for few of you guys, please do not just submit the screenshots. Okay. Do not try to copy as well. And when you are submitting the screenshot, please try to explain what you are submitting, what this screenshot is doing. For example, if I have this screenshot, I will say this is for ICMP redirect. Attack tool number is 86, and we are putting the new gateway, which is 10.0.2.7, so that the packet can redirect to this machine or host, and the source is 2.6. Okay, as much it makes sense. So here I can explain that, look, we are pinging from this client to the server 2.6, and the normal ping is depicted on the Wireshark as well, where the source and destination is this, and that's a request, and we are getting the replies. If you understand what you're doing in the lab, I've seen some excellent submissions. Very proud of those. You can write the story. Don't just submit the screenshots. No, that's not good. Okay. So this is my pointer for you. Yeah, I just want to give you marks on labs, and it's very easy to get the marks. So please don't lose them. Yeah, thank you very much. I'm just going to stop the recording now. And if you have any questions, let me know, please. Thank you.